And actually, it has the following structure. It is, so for example,
So this is also out of the frame.
yes.
Uh-huh.
Consider, say, CP1 equivariant ring. So there is this mysterious, or so there is this formula. So ring is generated by polynomials in sigma, and because of this residue formula, it's actually a ring of polynomials moduli this relation. So it actually has two generators. Has two, so this, sorry, it's two-dimensional.
So could you remind what you mean by semi-simple?
Sure. A ring is semi-simple if it has the following multiplication rule: no summation.
Mm-hmm.
In particular, ring, oh sorry, not P, C. In particular, a ring of polynomials is not semi-simple.
Mm-hmm.
A ring of polynomials divided by sigma k is also not semi-simple. However, this ring is semi-simple. Let me, and of course you know this ring. This is actually the ring of functions on 2 points. So you consider this as an equation.
Mm-hmm.
It has 2 zeros, and this is the ring of functions on solutions to equation.
Mm-hmm. Mm-hmm.
To describe it explicitly, I would say that any polynomial in sigma would be decomposed as this: plus what? Plus something that has value equal to 1 at particular point. So what has a value equal to 1 at 0? Of course, it's 1. But it has no dot zero value at m. So I want to ensure that it will have 0 value at m. So
we want sigma plus m divided by m. Ah, okay, yeah.
So actually 1 is not good enough, while, sorry, point minus m. Sigma plus m
Divided by m.
is
Mm-hmm.
good minus m divided by m.
Mm-hmm.
And here I put coefficient lambda 1. And here I have another thing. This should have a 0 here. So it would be sigma
Divided by
at
minus
the point
m.
minus m. It is
Mm-hmm.
minus m. And I
Mm-hmm.
want
Mm-hmm. Yes.
divided by minus m. Lambda 2. So any polynomial has this decomposition.
Mm-hmm.
So when I multiply this by this, I get 0. So when I multiply this on itself, so while Dong is not watching us, we can still make this experiment.
Mm-hmm. Mm-hmm.
Okay, sigma plus m, sigma goes away, so we are left with, goes to r. So we are left with sigma m over m squared, sigma plus m cancels out.
So, sorry, what are you calculating? You're calculating this first polynomial squared?
Yes.
Mm-hmm.
It is just a check.
Mm-hmm. Yes.
So when we square the first polynomial moduli relations, we are getting itself.
Mm-hmm.
With the coefficient 1. You see here, coefficient is 1.
Mm-hmm.
Similarly here, sigma over minus m times sigma over minus m. It is 1 over m squared sigma squared. So I add m sigma and divide them and subtract m sigma. I am getting this over m squared, but it's not that important, minus sigma over m. So I somehow made this simple exercise from algebraic geometry to show that we actually have this.
Mm-hmm.
And since we were doing localization and we managed to change or to move all equivalently closed observables, all closed observables into equivalently closed,
Mm-hmm.
without saying how did we, why it's true in general, we did it explicitly, right?
Mm-hmm.
Let me recall. That we had omega on CP1. So similar thing would go on CPN. Then we realized that we can go to the equivalently closed observable. Once again, D plus MIV. This is 0 4-dimensional reason. This is 0 4-dimensional reason. What is left? R. So there should be a minus sign here. If there's a plus sign here, minus sign should stay here. IV omega M minus DH. But this is exactly the condition that H is a Hamiltonian for the vector field V. Okay? So that's how it was.
Mm-hmm.
And this is justification of the formula. So, sorry, I want to say, so we realized that equivalently closed observables are omega plus M h.
Mhm.
Now we know that we can take it to the kth power. And we may very well use localization. So when we localize, we forget about omega. We keep only this thing. So so-called sigma to the k goes to m h, mk to the hk. So h is replaced. So now it's just another explanation of what happened without writing down this formula. We have mkh to the power k. So we have a sum. Here there are weights of points as functions of m. And here we have values of h at these points. So without this residue formula, this should be clear.
So sorry, I'm lost in what are we calculating here? I mean, why did we throw out omega?
I am illustrating the following idea.
So you wanted to localize what? Are you explaining the Sturm-Liouville
formula? I want to have another look at this formula without knowing this formula.
So Andrei, what is the starting point? What are you calculating? Are you calculating the Sturm-Liouville integral, or what are you calculating?
Yes, if you wish, I am computing polynomial of these observables. And I am integrating.
Okay.
Equivariantly. And then I say that that what I have to do is to sum over fixed points. Then omega does not give a contribution. Only function give a contribution. So I have two things. First, sum of the fixed points, then the weight of the pair, p fixed, weight. And then polynomial m h p fixed. So this formula is true, say, for any toric variety, for sure. Actually, not only for toric, but toric would be enough for us.
So in principle, it should be just a manifold with a circle action.
Yes.
One action of
one circle. But to use this formula, I need to know that all observables are generated by this. So what I need to do, I need to substitute in the polynomial. So suppose everything is generated by 1, by powers of omega, like for CPN. Then I need to take values of h at fixed points. I explicitly know it because I know the Hamiltonian. For the case of quadratic, for the case of CPN and other CPs, these are just very explicit quadratic functions. So I know their value. They are called heights. So picture for CP1 is like this. You have CP1, you embed it into three-dimensional space, and you know that rotation is generated by the height. You think that it is quadratic, but it looks quadratic because you try to write it down in coordinates on CP1. When you embed it, you know that here that it's a sphere, so you see that it's the third coordinate.
Yes.
Okay, so you know how to compute this. You can just ask how to compute this, the weights. So the weights here come from the weights of the action of the equivariant of this algebra, or actually group, in the tangent space to the fixed point. So you might try to see how to compute it. Actually, the way to compute it is like this. So in some example, you have C to the N over C star. Okay, so you take, you would be fixed point. This fixed point is actually a line. And you know the weights. You know the weights of all elements here. So something goes to gauge group, something goes to external. In equivariant formula, you need the weight factor coming from external. However, typically you know the total. You know how C star is embedded. So here we have C star to the power n that acts. How should I say acts? Acts is written like this. It acts.
No,
And
the previous one was correct.
This one.
With yeah.
Okay, and you know the embedding of C star gauge into C star n. So you know what is the tangent space. So tangent space is, of course, tangent space to a point. It's, of course, the factor of Cn, that is tangent space to any point, by the action of this C star gauge. So that is determined how this is embedded here. The same reasoning could work if we have more complicated gauge symmetry. So that's how I'm getting this weight factor. That is actually a product of eigenvalues of actions of these C stars in the tangent space. So I explain this formula without mentioning to any sigma, any contour, and any residue. So for my favorite c square over c star example, with c star square acting here with weights 1 and 1. So weights were 1. Okay, so in both cases weights were 1 and 1. So how should I write the weights? Yeah, I think it's clear that ETH acts here by delta IG. Now, we have the quotient. The element of the quotient is a line, right? Now let us see how elements of this c star square is acting on this line. I'm looking for weights. I'm just thinking, how should I, okay. How should I explain it in the simplest? Maybe when I say weights, I need to show it in the multiplicative form. Okay. So here I have zi, and the action is zi is going to zi e to the lambda, and here is the matrix I j. I don't like it because it looks like a power. No, and also, sorry. So the I goes to lambda. Parameter of lambda would be j. Okay. So the I goes like this. So I need to put the power. Of course, it goes to the I. I want to say that if j equals to I, it is 1. And if j equals to is not equal to I, it's not acting. So delta ij, I think that's the way.
That's fine. Yeah.
No summation. Maybe in this case, I'll do the general case. You see, it's the same. So what I'm trying to say is that there is a fixed point of this is direction. That is vector like this. So here we have these vectors. Fixed points. So here here I am looking at the tangent action, as the action on the tangent space. So somehow for me it is clear that that the main thing is acting by zero since it's a fixed point, while the rest are acting with the weight 1. Or -1. So let me see. I need I think with the weight 1. Let me see. There was an easy way. So sorry. So it's a point. Point goes here. Here is a nearby point. Nearby point goes here. No, I am doing. But then I need to project it. So it goes here. Okay, maybe I'm not writing the right picture.
So, Andrei, there should be also some specific circle, which, because you have one M in the picture. So you have,
yes, I have, yes. In this case, I described CP1, I had one M. Actually, there are several M's. So for CP1, there is a specific circle. I'm sorry, trying to do everything together. So CP1 is C squared over C star. And I have only one C star external. Okay?
So for CPN, you could have also in principle selected just one C star. You don't have to take all.
And it is exactly this C star that I selected. You want it here.
For CPN, you could also do that.
Yes, for CPN. For CPN, I can also do that. However, I'll get more information if I select universal. Because in this case, I will not mistake myself with okay, so I know, of course, the general formula. And the general formula is, so I know it here. I'll try to illustrate it here. So the general formula for CPN sigma minus m n plus 1. Because these are weights of C star to the n plus 1. So if C star to the n plus 1, so having C star to the n plus 1 in the total space, I could have Mhm. Mi IVI. Okay. So this is the equivariant.
Mhm.
Then, okay, in the language, so I'm sorry for changing the setup. In the language of gauged model, I say that mi are mi plus, and here I put phi or sigma for the gauge, for the group that is gauged. So when I do it like this, I just mean the diagonal is gauged. And then I take this integral. Now I want to interpret this, why this integral is correct without doing integral transformation. I'm trying to interpret it like this. I need to show that the coefficient here is exactly the weight of the external group on the remaining tangent space.
So is it okay that the formula on the left and on the right, on the left, one of the m's is 0?
So you see, in this integral formula, you have a shift.
Mm-hmm.
All m's could be shifted by a constant.
No, I see. But so you're saying that the definition of sigma is different on the left and on the right, that it's shifted between the two.
Yes.
So the parameterization of polynomials in particular is different. The polynomial observables.
Yes.
Mm-hmm.
So now, as you mentioned, when we pick up a fixed point, say sigma equal to m1 here, we see the following weights: m1 minus m2, m1 minus m3, etc. m1 minus mn plus 1. So group that is acting, the external group, is of course C star mod C star to the n mod C star. So actually there are many ways. So there is no canonical way to choose a basis here.
Mm-hmm.
Okay? It's a factor.
Mm-hmm.
However, since we already have chosen a basis here, we can choose a basis here. I think so.
Mm-hmm.
So these are the weights on the quotient space. because what you say here is that the weight of M2 has to be negative with respect to the weight of M1. So this is exactly the weight of the homogeneous coordinates. Etc. So maybe this is the better way to show. Maybe this is the better way to show what is the tangent space.
So weights are integer numbers, are vectors of integer numbers, and these m's are whatever they are, some formal variables.
Yes, you are right. They are variables. So so what I mean the weight of the external group, not the gauge group, but external group.
Yes, yes.
So this is, of course, parameters of the external group multiplied by weights.
Okay.
So
yeah.
consider, for example, non-homogeneous coordinates z2 over z1. The group that multiplied z1 z2 lambda z2 is a gauge group. So it's not acting here. The group that multiplied z2 to e to lambda z2 and the group that is not multiplying z1 acted by 1. Similarly, this, so what is this? So what is this M1 minus M2? You take Z2, you take Z1 over Z2, okay? So you are multiplying the first one, lambda to the power M1, and here it's how Z1 is multiplied. And here you have lambda to the power M2. So altogether you multiply to lambda to the power M1 minus M2.
So we got some non-integer powers.
Of course. So yes, this is my fault by not explaining what these m's are. So so just imagine the general abelian group C star. Okay, maybe it's a way how to say it. C star embedded to C star to the power n. I will try to embed it in the following way. So it takes lambda. Generator. Generator of the group lambda m1, lambda mn. This is this column. So this belongs to C star to the power n. This embedding corresponds to the vector field. That is mi.
I'm very, Andrei, sorry, I'm very confused. I thought that there is some, that weights are supposed to be integral, and now you're saying that m's are weights.
So that, okay, sorry. It's my bad. It's my bad phrasing. I'm very sorry. So I'm trying to interpret the following thing. Suppose I have a space X. So suppose I have the action of U1 to the power n on X. Okay. To say this, I have to select vector fields V1, Vn, each corresponding to the group U1. Okay? Now, let me pick up set of numbers, complex numbers. Mi. I going from 1 to n. Now, let me construct a differential, D, equivariant. That is D ordinary plus Mi contraction with Vi. So we have this differential that depends on M. Then I don't want this to be upstairs in order not to mix it with the power. Here sum from 1 to n. Then the equivariant squares to Mi, sum from 1 to n, Lvi. So it is 0 on invariant forms. So this allows me to study cohomology everything as a function of this M. Okay? Now, so this was on the space X. Now let me assume that I am studying the quotient space. Say I take a quotient with one U1. It's possible, yes? Then it's interesting that that here I can consider equivariant differential with respect to, so here not all IV are independent. Okay?
Yes.
So it means that so how should I say it? I should say it like this. Mi, this vector M, belong to the algebra dual, right? So now this differential actually depends not on the vector M, but on the vector that belongs to what? So let me see. So here I have a quotient that acts. So here, now on the factor, I need to consider a sub. So quotient goes to subspace. So it means that M, that these M's, so there was a gauge, Lie gauge, I'll call it this, should equal to 0. So only this acts. So that's why I am studying the cohomology of such differential, where M is restricted to this condition. In particular example, where we have CPN, that is Cn plus 1 divided by C star, the space of M belongs to, I can say Cn plus 1. And now here I get condition that M2 gauge equal to 0, and this G is actually this vector.
Yes.
So solutions to these. So I have solutions to this. So they have a basis like this, differences.
Mm-hmm.
So if I pick up and there is no canonical choice.
Mm-hmm.
To get a canonical choice, sometimes I can have a canonical choice. To get canonical choice, I may consider fixed point. So this fixed point corresponds to what? So how to say it? So, okay, in the case of CPN, I understand it. However, I have some problem to say it in general terms. So when I have a fixed point, it breaks my symmetry. One second. You see, I know the answer. I'm trying to formulate it mathematically. So here, the answer would be that when I take a fixed point, I have this m1 minus m2, m1 minus m3, etc. And I understand it as a preferred basis. So this is a preferred basis in the space of solution, in the space of solutions. I'm thinking how to explain it naturally.
I think it sounds very reasonable.
So it means that near the fixed point, I have a decomposition of D equivariant in terms of these. Actually, what I see is that so this is substitution. So I need to explain what these are. Okay, let me say to you an example, and then maybe we will see. I have the set of coordinates like this. I have a fixed point. On the quotient space, I have assets I have locally, non-homogeneous coordinates. The I over the 1, I greater than 1. So these are coordinates. Near this fixed point. These coordinates have differentials, okay? Differential of the I over the 1 is dzi over the 1 minus the 1 square the I dz1, something like this.
Mhm.
So am I right? So well, let me see. You see, I'm trying to explain. You see, maybe I'm getting it wrong. I'm trying to explain what is the action of the external Lie algebra in the tangent space to this point. Okay.
Mhm.
You see, I'm struggling in writing down, in getting explicit explanation
No,
why these
Mhm.
are the weights.
I think it sounds very reasonable by now.
Why this is not the weights, why these are equivariant volumes, I'm sorry. So when I say weights, of course I meant equivariant volumes.
Mhm.
Okay. Well, so let us take a break, like 5 minutes break.
Okay. Okay. Mhm.
Okay. So actually, these exercises were to be able to compute the following. Once again, space of quasi-maps. So let us still try. C square over C star to C square over C star of degree D.
Yes.
So last time we said that we have this.
That was degree 1.
Yes, so
Now
this was degree 1. C0, 0, Z0 plus C0, 1, Z1. So the action of these two C stars so we have the action of these two C stars, and we also had C star external, and here we also have C star external. So here we have a covariant parameter epsilon. Here we have a covariant parameter m. So the space is CP3. So in the formula for a covariant volume, we had the following. So we had sigma plus epsilon, sigma plus m, and sigma plus m plus epsilon. So we had contribution. So I'll write it like this, and I leave this open at the moment. And here we have contribution from the 4 fixed points on CP3. So now, let us do the following. Let us see how this moves forward to degree D. So let us do degree 2. So when we have degree 2, let us write down everything very explicitly. C00 to see what's going on, Z0, plus C1, 10, Z0, Z1, plus C1, 11, Z1 squared. And similar things downstairs.
Mhm.
C0, 11, Z1 squared. Now let us see how so I'll erase this. Let us see how the gauge group is acting. So we have two gauge groups. Once again, once again, this group, gauge group, act like this. So where Z0, where Zi went to lambda Zi,
Mhm.
this C has weight 2. Okay?
Mhm.
Where Yi go to lambda Yi, the C has weight 1. Okay. So we see that the action of one group and another group, gauge group, coincide.
Mhm.
However, it's not the case for the action for the rest, for the external group.
Mhm.
Okay? So external groups are Z0 going to, so what would be the best way to write it down? Mhm. The best, so according to the previous experience, the best way to write it down would be to have two epsilons here, epsilon naught, epsilon 1, and two m's here, m naught and m1. So let us see what is going on. We will have 6 terms in denominator. So before we take a quotient with respect to this, we can write equivariant volume with respect to the total group. It is with respect to m. So every time I'm getting 1 over m. Okay, sorry, let me write it down. M0 plus two epsilon zeros because of the power 2 here. Here I have m0 plus epsilon 0 plus epsilon 1. And here I have m0 plus epsilon 1, 2. Similarly, I have here. So here I'm just writing out the eigenvectors of the vector of the action of the not eigenvectors, eigenvalues of the universal action. So here are eigenvectors of this field. This big V is the Lie algebra vector field of the total Lie algebra containing both external and internal acting on these C's. Okay. Now I need to
find sigma.
Yes. Now I need to identify sigma. So how should I identify sigma?
Well, it's hidden inside m's and epsilons, I guess. And,
Yes.
yeah.
Yes. So it is hidden everywhere. So I think it's like this. And I have many ways. So and of course so I have CP5. Okay. So the amount of the fixed points of the most general C star is 6. And here I see that I somehow get them all. So so then it would be interesting. By the way, we will get CP6 also if we will consider degree 1 to CP2 clearly. However, weights would be different and they will have different meaning.
Mhm.
So let me try to leave it as a homework that we will discuss next time. I mean the meaning of the contribution to each particular fixed point. So what does this localization mean? So, if, by the way, if you look at it this way, you may say that it is possible to eliminate. So here we have two epsilons. So because of possibility to shift in sigma, we can go always to difference epsilon naught, epsilon 1, and call it epsilon.
Mhm.
And this has a clear meaning of C star action on the source. And this has universal sense. And this is related to psi classes, but unfortunately today, but I'll explain it not today. Because today I want to move to, so after, you see, after I explained how this could be done, one can try to see what could, that this is generalizable. So this is how this could be generalized to D, and it's clear how to write the general D formula. And this is kind of Giventhal formula. But before we go further with the Giventhal formula, so it's Giventhal D equals 2 formula.
Sorry, what is D? Is it degree or dimension?
D is degree.
Mhm. Mhm.
So this formula here has different parameters. One parameter is degree.
Mhm.
One parameter is dimension. So it is, but this is for CP.
Mhm.
Okay, let us try to write down similar formula for target being not CPN, but say CP1 times CP1. Okay?
Mhm.
In this case,
So it should be a double integral now instead of a single integral.
and here the answer seems to be yes. Let us see. It's because the answer is like this already in the case of of degree 0.
Mm-hmm.
So here we have y1, y0, and here we have, so z is used, y tilde, I have put it y tilde. So you can just, you are just writing down. So, okay, so it is kind of a general case.
Mm-hmm.
y1, y tilde, 0. So you just write c tilde. And of course, it's clear that before you put thing that you call sigma, you have the product, because C's are the product. Now the difference is that while you have clearly two sets of M's, and M are parameter corresponding to the target symmetry, you have the same epsilon.
Mm-hmm.
So maybe it will be instructive. Okay. So let us try to write down what it is. Here we have okay, M1 plus, okay, and we have two sigmas.
Mm-hmm.
Sigma, it will be called sigma and sigma tilde. Sigma plus M1 plus 2 epsilon zeros. Okay?
Mm-hmm.
Sigma plus M1 plus epsilon 0 plus epsilon 1. Sigma plus M1 plus 2 epsilon 1.
Mm-hmm.
Here we have sigma plus M1, so it was the second, plus M0 plus 2 epsilon zeros, etc.
Mm-hmm.
Downstairs, we have sigma tilde. However, this sigma tilde has M1 tilde, but the same epsilon. Okay. Moreover, in this case, we can have by degree. We can have degree d equals 2 here and d equals 1 here, for example.
Mm-hmm.
And in this case, it will be like this. I'm just writing this thing as an example.
Mm-hmm.
Epsilon 1. Sigma tilde plus M0 tilde.
So indeed, there's a cutoff. There's a cutoff of the camera. Uh-huh.
Plus epsilon 0. Sigma tilde plus. So it was the second one, epsilon 1. And here is the integral over d sigma tilde. Then you may ask, is it a product? No, it's not a product. It's not a product because in this expression and in this expression, epsilons are the same. However, m's are different. Now, it is clear how to modify it for the case of the blown up target. Okay. That we also described. Remember, we said that besides CP1, we can, or CP2, we can consider CP2 blown up. So, in this case, we have what? We have C4 over C squared. Okay. So this would be a target, two-dimensional. So remember that there was a choice of weights. Now some of these weights were negative. May I leave it as an exercise? But it would be instructive to see the blow up in these formulas. In particular, say in degree 0 case, so what I am blowing up? I need to check what I am blowing up. Because I can blow up C, I blowed up C squared. I can blow up, okay. So this is CP2 with 0 blown up. So it should be C4 over C star squared obtained as a quotient. And there should be contribution. We need to figure out contribution from 4 fixed points. You may ask, fixed points of what? C star square external. So in this case, in this way, we will try to describe how to blow up a target. And I think it's good to make up this exercise to see the weights for yourself. Although not weights, sorry. It's not my mistake. It's my mispronouncing. So instead of saying contribution, I'm saying weights. Sorry.
Mhm.
because contribution is a weight times the parameter.
Mhm.
You see, for me, this is I mistakenly call these weights. However, it is a contribution obtained by weight multiplied by parameter. By the way, I don't quite like this this light coming in. I'm sorry. You should tell me that that this is not good.
It's all right. The formulas are visible.
No. It's one second. I'll try to fix it up. Okay. You see, I made it.
Mhm.
So now, let us do more interesting stuff. Because when we modify target, you may say, okay, so we are repeating what other people were doing. It's not that practically interesting. Now, what is practically interesting is to modify the source.
Mhm.
We started this description, but now we can write down equivariant, so-called equivariant volumes.
Mhm.
So first interesting example is C cube over C square that goes to Cn. Okay. So how can we write down this? In a very similar way.
Mhm.
So I am pleased to see that while dimension of the source grows, the complexity of the problem is not growing. Okay.
Mhm. Mhm.
So I'm pleased to see this. Now I'll use the same letters, the same coordinates. Sorry, y0 equals what? So it should be a linear function. So let us study degree 1. By degree here, I mean not what normally people say. I mean that it comes from the polynomial map from here to here. And the polynomial map, if it's homogeneous, comes into degrees. So y0 is in the target C0 0 Z0 plus C0 1 Z1 plus C0 2 Z2 y1 C1 0 Z0. Okay.
Mhm.
C1 2 Z2 y2. Okay, etc. up to n. So how complicated this is? It's not that complicated.
Mhm.
It's basically of the same thing. So we still have the same C star. We have weights of, and of course we have here C star external square. And we know how to get this C star external square. We get C star external cube, that is clear. And we use the sigma presentation. Similar thing could be done here. So now, this is 3n, so it is Cp 3n actually minus
1. 1, yeah.
Okay, so in particular for n equals 1, Cp, no, so when n equals 2 is interesting. It is Cp5. Once again, 6 points. Now, how to write down the action of the gauge group from the left and from the right are the same. So it means that we do not need to bother too much. The action of external group. So we have 6 terms. From C00, we know that it is this sigma plus what? Plus epsilon 0, okay? Plus m0. Sigma plus epsilon 1 plus m0, etc. Sigma plus epsilon 6 terms. Sorry, I can write down. Epsilon 2 plus m0. And all the way down, sigma plus epsilon naught plus m and sigma plus epsilon 2 plus mn. Or I can write this term. Sigma plus epsilon 1 plus mn. And we have a single integral. Okay. So now, okay, so we may compute it and we may try to interpret it, because previously we were trying to do this and we found that there is inevitable blow up. So I think that everybody is interpreting things with his own speed. Okay. One has to sit down, write down pictures, find for himself what is going on, how to interpret this term. By the way, it is clear what is going on if we grow up a degree. Nothing terrible would happen. The number of terms of grow up sigma would be the same. Okay. Still a single integral. Still, all terms are available and explicit. One can try to think also what would it mean to have CP when n capital is 1. It's also possible, however, I never did it. So if n capital is 1, so it means, sorry, if n capital here, so 0 to n, means if n capital is 0, what would this mean? Formulas are clear. So what are these 3 coefficients? So in degree 1, so what are 3 numbers when we divide by C star? So let us look. Consider case. N capital equals to 0. There is nothing here. It is CP2. And yes, CP2 is actually what? It has a meaning. It is a space, A lines. In CP2, as far as I understand, remember. Okay, is it true? Because you see, we consider this 3 numbers. Divide by C star. Yes, it's a line. So it's a line in the source. So when we compute, equivariant volume of the lines in the source. It's kind of interesting. But it would be something for the lines in the source. You see, here they have some tricky epsilon. Parameter. So if you just look at it as the space of lines in the source, you would probably not see this dependence. So now let us see. How does it look like? So this M0 goes away because you can shift sigma. So it was expected. So you may think, what does this mean? Not only M naught could be erased, also we can write down, we can eliminate epsilon naught. So after we eliminate epsilon naught, we will get contributions from two epsilons, epsilon 1 and epsilon 2. And by the way, it is clear that you will get weights. Sorry. You will get, not weights. Pasha, sorry. Contributions. Ah. Now I know why I call it weight. Because for me, weight was not the weight of the action of the group, but the weight, how you weight fixed point. You sum over fixed point, and when you sum over points, when you have a weight. So that's what I call weight. And this weight was also expressed in terms of the weight of the group action. So it is a place where misunderstanding happened. So here we are. But we know how to treat it. We have contributions of each particular point. With some weights, with some contributions. So in particular, sigma equals 0. For sigma equals 0, you have the factor 1 over epsilon 1, epsilon 2. And this is exactly Nekrasov factor. So when Nekrasov studied the modular space of instantons, his first result for a single instanton was this. And of course, it is the weight. A weight of what? It is a weight of CP2. However, here we have this weight in a very non-Nekrasov way. In Nekrasov way, it was an instant. We had an instanton on the source, and the instanton was going all around the source, and we said, look, it's a volume. In the particular case, n capital equals to 0, we do not see a point. In the space that people used to call instanton, but we have exactly the same formula. For the leading contribution. So this is contribution from sigma 0. Now you may try to guess what is it a contribution for? How to understand it? Now we have also two other corners, and of course you know that the sum of residues would be 0 because we consider compact. space. Now, how would we like to consider non-compact source?
Well, this should correspond to a different contour.
So, and how to treat it? So here I have a conjecture that I have not completely justified.
Mm-hmm.
Saying that in some sense, picking up different points, maybe with some weights, should correspond to non-compact source. Unfortunately, or maybe fortunately, I have some unclear points here, but would it be point like instantons? I would say that such things show that they concentrate near the fixed points in so-called omega background. What's interesting is that here I do not have, so from the description, I have rather a line than a point. Nevertheless, the answer is similar. So let me come to toric description. We know, Pasha, we studied it in another seminar, how to describe a line. It is this.
You mean tropical description?
Tropical description. So this is a line. And when you look at the line this way, could you see where is the so-called instanton is hidden here? It is here. So previously we just computed it. 1 over epsilon 1, epsilon 2 looked like Nekrasov volume. Where is the point here? And the point is really here, such that it's volume.
Sorry, Andrei, I don't know what you're talking about. I'm sorry.
I am talking about the following. I consider this space. This is a space of degree 1 curves. In the source, not on the target.
Yes, yes.
I compute equivariant volume according to the formula. And I see that it is a sum of 3 contributions.
Yes.
So since there should be contributions, and they look pretty much like contributions of the point on the source manifold. Because 1 over epsilon 1, epsilon 2 is the equivariant volume of C square.
No, but those are tangent spaces to CP, whatever the space of lines.
Yes. Yes.
Right.
They
So,
are equal. Yes.
So each tangent space looks like C2. Is it correct? Yeah, looks like C2 with sort of a point in the middle. So isn't that?
In some sense, yes. Yes.
Mm-hmm.
Okay, I'll try to explain what I mean.
Mm-hmm.
Maybe I posed it the wrong way. So we computed the space of lines, okay,
Mm-hmm.
not knowing exactly the structure of this space of lines.
Mm-hmm.
The answer looks, so we write down formulas,
Mm-hmm.
making shifts, and we see that this is nothing but the equivariant volume
Mm-hmm.
of CP2. And of course, since we have these epsilon parameters, it corresponds to, so this CP2, we cannot mistake this CP2. This CP2 has something to do with the source.
Mm-hmm.
So this formula suggests this formula and also its limit that somehow integral over the space of lines should correspond to the integral over CP2 of position of points, of position of a point. Because here we see the position of a point. And CP2 is the same. In order to see this, that it actually happens, we tropicalize. So when we tropicalize, we see that lines actually correspond to points. So lines, so this formula is valid in particular because in the tropical limit, lines correspond to points. And to integrate over lines would mean to integrate over a position of this point. That's why the answer is the same. So this is the way to use equivariant integrals. They predict you some formulas that may someday have geometrical explanation. Once again, this equivariant formula for the volume of lines.
So Andrei, this lines and points, isn't it just the same as for a Grassmannian of one-dimensional subspaces in three-dimensional space? It's the same as Grassmannian of two-dimensional subspaces in three-dimensional space.
Let me see. So maybe, you see, the same formula could have, so the same formula could have many interpretations.
Mm-hmm.
Okay? In particular, if we go further and study degree 2,
mm-hmm.
So let us do it to get some feeling of what we are computing. Okay, so there will be many terms. So I will not write zeros. Okay, everywhere is zero. Y0 is. So here I have 3 variables, degree 2. So total number of terms would be how much? Okay, okay, okay. It will be okay. No, I still have to write it. So so now I want degree 2. C0, 0, Z0 square plus.
It's 9
Z0,
terms probably or something.
Okay. So how many terms would I get here? C0, 2.
I think
Okay.
9 terms.
You say 9 terms.
I think so.
So 3 of this type, and of this type, I'll have 3 times 2. Yes, 9 terms. Okay. So it is, so this space is C9. C9 divided by C star. So it should be CP8. Okay, so we have 9 terms downstairs. And what are the only weights? It will be d sigma. Sigma plus epsilon 1. Sigma plus epsilon 2. Sigma plus epsilon 1 plus epsilon 2. Total degree should be 2. Okay. Yes. So there will be 9 terms downstairs. And it looks like, so, and so let me write, still I want to write it down. Sigma 0, 0, sigma 0, 1. Just now, sigma plus 2 epsilon 1, sigma plus 2 epsilon 2, yes. 1, 2, 3, 4, 5. Somehow I get only 6. So does it mean that that I'm missing something? I truly get only 6.
Let's see. No, maybe you're right. Maybe
like this, and with 2 different, you also have 3, not 6.
Yeah, no, I think my count was wrong. Yeah.
So total is C6. 1, 2, 3, 4, 5, 6. Okay. So it means that I have 5 points. Okay, so it means that I cannot interpret it anymore as 3 points. And this is because we have the following tropical description. So this is degenerate, 2 points. So either it's 2 points plus something else. 2 points means 4 plus 1. So 5 is 4 plus 1. 2 points and degeneration. Or if we draw it this way, we see 4 points. That is 8 and 3 relations, minus 3. Okay. So it's not a 3 point anymore. So maybe this is the first formula. So this is the equivariant volume of the space of such configurations that correspond to degree 2 quasi-map to nothing. So this formula also suggests how to write down more general formula. If you have a toric manifold, you can try to generalize it in terms of polytopes. In particular, it is very instructive, I think, to study the following situation. Make a cut somewhere here. So the tropical curves on the total space come from tropical curves here and tropical curves here.
Mm-hmm.
The question is, could we make this precise? This more precise. So, altogether, I want to resume. I want to make a resume. The resume is that equivariant volumes and their decomposition into contribution of the fixed points is doable. It's a simple combinatorial formula for any source, for any toric source and toric target. It's not a problem. The interesting problem is to get a geometrical interpretation of the contribution of each particular corner. That's one thing. Second thing is to see what happens if the source is cut, not in an arbitrary way, but in a way that preserves its toric structure. So this is the main difference between cutting of the source in quantum field theory and here. In quantum field theory, you have an arbitrary way to cut your source. And it's very hard to describe the corresponding structures. Here, only special cuts are allowed. So you cut toric into toric. And you hope that equivariant volumes are related. And later on, we will try to find out observables that behave properly under cuts. So that's what I wanted to tell you. And let me ask you to play in with this. Study some particular cases yourself. Get your own geometrical intuition. Use the tropical generalization that may help you to understand what is going on. So basically, this is about the so-called special functions. In the game. So we did not consider non-abelian groups, but only abelian groups like C stars are here. However, my feeling, my conjecture is that all necessary structures could be seen with already here with abelian groups. Okay, so that's it.
Right. Thank you.
So please spend several days trying to think about it. Okay.
Right. Right.
Yeah. Thank you very much, Andrei. This was very interesting.
Thank you. Thank you.
You are welcome.
Thank you for the lectures.
Okay, I hope that you will bring Dong. I hope that you'll bring contribution on the next lecture, in particular in the issue of factorization. So we came up with a very interesting issue of factorization.
Yes, actually, that's the point where I am very interested, and I really don't know how the things happen. So, looking forward to there's
I
something
think
else.
You see that factorization should be somewhere around here, because equation seems to be written in terms of factorization. Oh? Okay.
You see.
All right.
Thank you.
Thank you.
So then, see you next week.
Okay. See you next Wednesday.
Yeah.
Bye.
Thanks a lot. See you next Wednesday.
Bye.
Bye.